the last class we were looking at this output impedance calculation, and we studied how to determine the impedance of a circuit seen from a specific pair of terminals. Okay, so if I have some sort of circuit, a two-port network, something like that, what we did is that we just we were just looking at how to compute the impedance seen from a specific port. Okay, so that is what we were doing it in the last class, and for that we had followed some specific set of rules. So the first rule is to connect some sort of voltage source, which is Vx, to the port, and then later what we did is that we were suppressing the or kill all the independent sources. Okay, so this is what we were doing it. And the third one that we are doing is like we were trying to measure the current Ix that is flowing out of this Vx. Okay, and then later from that Ix value we were trying to compute the resistance Rx, which could be defined as Vx by Ix. Okay, yeah. So now what I did is, so the very first point is to make sure that we are connecting some voltage source Vx, and then any type of input source that we had, we were trying to kill them. If it is a voltage source, we were trying to kill them by a short circuit, and later on we were trying to measure the current Ix. Okay, so these are the three major rules that we followed in order to compute the output impedance. Okay, so now what we do is that let me quickly ask certain set of questions so that let us see whether you could be able to answer based on these 3 points. Okay, now for this I'm just going to consider only 3 terminals here: drain, source, and the gate. And whenever I'm trying to look at a particular terminal, I'm going to assume the other 2 terminals are at the ground. Okay, so if I'm looking at a specific terminal, I'm going to assume all other terminals at a ground. Okay, so now let me begin. So what is the impedance that we were having when I look through the drain, provided the other 2 terminals of gate and source were connected to the ground? R0. Okay, so yeah. So now again, so what happens when I look through the source? Yeah, 1 by Gm or Gm prime. Gm prime. Okay, so which is nothing but putting one more factor in parallel with 1 by Gm. Okay, yeah. So what about this? Infinite. Okay, because the current cannot go through the gate terminal, right? So obviously the value of Ix is basically equal to 0, so Vx by Ix is supposed to give us an infinite. Okay, yeah. So now, having done this, let us go for a circuit which is a diode connector. Okay, yeah. So now in this case, there are only 2 terminals, and when I look through the drain, what is the impedance that we were looking at? Okay, 1 by Gm parallel with R0. Okay, so what about this? Will it be same? Okay, so I'll begin with 1 by Gm parallel R0. Yeah, so there is a body effect because the source will not be at the ground. Okay, whenever we look at the source terminal, we are trying to apply some Vx, due to which the source will be completely at a different potential than compared to the body. Okay, so we need to include this extra term with it. Yeah. Now, we were also looking at one more circuit, but I don't know whether you can recollect because I did it with a hurry. Yeah. So what happens? What about the impedance that we look through the drain? What happens to this resistance Rs? Yeah, so one of the major thing that we can have in our mind is that the resistance would then magnify. Okay, by what amount? It depends on the intrinsic gain of this transistor. So that much if we could able to build in, then we can just add up the extra terms that has to be added. Is that clear? So for me, remembering the formulas is quite difficult. Okay, so I confine myself such that I use the small tips in order to build the entire formulae. Okay, so that is how I remember all these formulas. Okay, so now that I know that this resistance Rs obviously has to get increased or been magnified by the intrinsic gain. So due to which the formula is approximated to be something like Rs being magnified by the intrinsic gain of this guy, which is Gm R naught. But we know that the source is not exactly at the ground, due to which obviously it leads to a GMB factor, right? Yeah, so what I can do is that I just add a prime to it. So that completes the approximated formula for it. But this is not the complete expression for this R out. So what else has to be added? Yeah, so if you could be able to think, there is also a resistance here, there is also a resistance here. So add up those two resistances to it, okay? Yeah. So the actual formula, along with this term, we also have some sort of R naught plus Rs, okay? But in general, these values is quite smaller than this particular first term. So due to which we would approximate this entire expression onto something like this, okay? And we'll be mostly using this formula when we look at circuits from unit number 2, okay? But for unit number 1, like you can use this formula as your primary expression, but as we move on to unit number 2, then we can use this, the short form of this, okay? Yeah. So any doubt in this deriving this expression? Did you have any doubt? Okay. Okay. So now that let us go for one more circuit where I didn't derive it, but I just gave you a hint of the answer for it, where I had a drain resistance, but now that I'm just looking into the source terminal. Now what happens to this drain resistance? So yeah, so in the previous case, we had a different circuit where we were looking into the drain, and when I look at the source resistance, this source resistance was being magnified by the intrinsic gain, and that is the clue that I had, okay? But this time I'm just swapped both these components, okay? So now that I'm looking into the source, but I'm looking at a drain resistance. So in this case, obviously it has to be exactly in opposite phase, okay? So I just said that it is something like the drain resistance would then be diminished by the same factor of Gm times or Gm primes thereof R naught, whereas this guy was being magnified by this quantity. Now that I just want to prove this, okay, without proof I cannot say that it has been diminished, right? So what I do is that let us try to draw the small signal model of this and then try to figure out the exact expression, and later we'll just step down to this approximated result.
Sir, body is connected to ground.
Yeah, any NMOS is all connected to the ground. Even in the case of a PMOS, it would be connected to the VDD, but when I translate those transistors into small signal model, obviously the bodies will be grounded, okay? So it doesn't matter at all. Clear? Yeah, so now in this case, would you try this or? Okay, what about others? Yeah, so try, because in the evening probably I still have to get permission from HOD, so once she permits me, then we can go out. We'll be having a kind of activity in the hotspot near to the department, okay? So 2 will be in a group, and I'll be issuing some sort of sheet so that you'll be answering that. I think this has happened for, I don't know, C-section, yeah. So the same thing would be done, okay? Okay, so let me try to draw this small signal model. So I have this gate, the drain, and the source, and here is my VGS with plus and minus polarity, and based on this polarity I'm just going to draw the current direction, which is flowing from drain to source, and GM VGS, and for simplicity I'll just drop this GMB VBS, okay? If you want I can still add it, but again I'm not good at drawing it, so it will mess up my circuit. So I just use this R naught here, and from the drain you see that there is a resistance. One end of the resistance is connected to the drain, whereas the other end is connected to my VDD. So what happens when I translate this VDD to my small signal model? That goes to the ground. So due to which, from the drain, okay, the resistance is connected towards the ground. Okay, so this is where I have, and over here I have connected something like a kind of composite signal. So due to which I extract only the small signal out of this VB, and this is my small signal model. Now to this I have to first apply my first rule, that is connecting my Vx across the node at which I want to identify the impedance. So I've just connected my Vx. The second rule is to kill this input or independent source. So killing this is nothing but putting it to the ground. So I've done that. Now just try to figure out whether the value of VGS has gone to 0 or not. Okay, so let us try to evaluate that. Now when I look here, the gate is connected to the ground, but what about the source? Yeah, it is connected to my Vx. So due to which this entire potential would then be written as minus Vx, which is not equal to 0. So whenever this VGS is not equal to 0, obviously this current source would exist. Clear? Now again, we can do the same for VBS. We would end up having same thing, okay? And even that current source has to be added in the same direction. But I have not done it just because of the my ability in drawing it, okay? Yeah. So otherwise you need to have that as well. So now the current is actually is coming here, and then it gets diverted in two other directions, okay? So there are 2-3 ways by which I can address the same thing. Probably the guys at the end had asked me to do in a different way. So what I do is that I'll just start from the Vx itself. Let us look at the Vx expression and then see how this Vx expression is getting mapped onto my resistors. So now this Vx expression is from this point to this point, has been mapped right from this point to this point. Am I right? So it is something like this Vx is nothing but it's getting dropped across this resistance R0 as well as getting dropped across the resistance RD. So in short, the Vx is nothing but it's a summation of two components, drop across R0 plus the drop across RD. Now if I know what are the currents that are flowing across them, then it becomes easier for me to write the expression for this drop across R0 as well as drop across RD. So now let us try to figure out what currents are flowing across this R0 so that I into R0 will give me the voltage value. Am I right with it? Are you clear with this? Or you want to write it in terms of Ix? That also can be done. But the point is that I just want to go in a different way. Okay. So now what currents is flowing is something like there is a current. This GM VGS will always loop. So it finds its loop somewhere here. So it loops around this particular path. And apart from that, there is also one more current that is being pushed. So we know that this current Ix cannot be pushed into a constant current source. So the current has to route through this particular path. And then after then, what is happening is that this Ix would then flows through this and then gets back to its negative potential. So again, both these currents, you see, the GM, I could have used a different color. So GM VGS is again finding a loop and loops around it. And even this current, Ix, is also finding a path and loops around back to its same origin. Is this phenomena is clear to you? Any doubt? Okay. So now due to which, what are the currents that are flowing across this R0? Yeah, so I have this Ix plus GM VGS, okay. So how the current flows in the sense from positive to negative, and again when this is flowing, it has to be written something like this, the drops, okay. Plus the current is flowing through this RD and it is Ix into RD. So this entire component would then give us, why R0 will come? Oh yeah, I forgot here, yeah. Okay, so this is how I can write it, and later what I can do is that I can replace this VGS with minus Vx, am I right? So I just go here and then you know the result, so I'll just push it here, 1 plus GM R0 Vx, and over here it is just the summation of R0 and RD. Okay, so I've just simplified here, nothing fancy here. Now you got the result in a very simple steps. So I can write this Rx as Vx by Ix, and that gets me the value of R0 RD divided by 1 plus GM R0. Okay, so some of you had shown me the result, but I couldn't really verify it just because I don't remember the expression. So if you are mapping to the same expression that you have got it, it's right. If it is different, then something else has gone wrong in your expression. Okay, so is this fine, or you want me to derive the same thing in a different way, completely different way? Yes? Okay, that's supposed to be not a part of my work, but still I do that. Okay, so this Ix will work with the Ix rather than with Vx. Okay, so now obviously I can write in the fashion that we are doing from the beginning. Okay, so I just use this Ix getting split into two parts or something like that. So I can write this Ix as summation of two components. Shall I use a different color? Okay, so one of the current component is minus Gm VGS, and the other component is the current that is flowing from this potential to this potential. So across the R0. So how will I write this current that is flowing across R0? It is Vx. No, this is not at the ground, right? So it is Vx minus Vd. Yeah. So it has to be written as plus Vx minus Vd divided by R0. Okay. Now what is Vd basically? How will I express this Vd? Yeah. So both these currents which were being splitted up, it actually combines here as Ix, and this Ix is the one that flows through the Rd. So again you can write it as Ix into Rd. So again when you do the substitution, you would get the same result. There won't be any change between the results. So at least from here you can just carry on. Just see whether you're getting the same results or not. Are you getting the same results? So in case if you're working it out? Yeah. So whenever we find this resistance, mostly 99% we will not have any negative values. Okay. So I'm just holding that 1% just for specific reasons. If you really want to mimic a negative resistance, it is possible with active devices, but we will not touch upon this in this entire course. Okay, so for this course, we will always assume that the Rx value will have to end up having some sort of positive result. Clear? Yeah. So now that I've got this result based on the circuit that has been shown here, so I'll just copy the circuit. Yeah. So now that whatever I said is to be defined right now, right? So I said that this Rx could be further written as R0 plus 1 by Gm R0 plus Rd divided by 1 plus Gm R0. So what if I'm considering my body effect into account? Will it be the same result? Yeah, so I hope that I don't remember it. You can just verify whether you are getting the same result or not. Okay, so I'm not pretty much sure about it, but mostly I guess that it's supposed to be Gm prime, which is nothing but Gm plus Gmb. Okay, so see that whether you're getting the same result. Yeah, if it is so, then what I can do is that I can further go for some simplification, because still it is not an approximation, it is just the same result. But now what I can do is that I can just assume that my Gm R0 is much larger than the value of 1. Now when I consider that condition, what happens to the first term in my expression? Yeah, so it becomes something like 1 by Gm prime. Okay, and then I'm just going to have something like this quantity. Now in general, this 1 by Gm term is quite smaller, so one could further, if it is smaller than the value of 1, then I can further approximate this to be something like this. Okay, and that is how I get the result. So in a way, I can build this formula just by knowing that whenever I'm looking through the source, the drain resistance would be diminished, or the other way is whenever I'm looking through the drain, the source resistance would be magnified. So these are the two things that I will take away from here. Okay, so that will help me to finally build the entire formula rather than thinking like what exactly the formula is. Clear? Yeah, so now in the last class I stated that apart from finding the output impedance, we also have to find out one more quantity. What is that quantity that we need to find? We went on to a gain expression, because a gain could be defined as a product of two terms. What was the first term? Yeah, so I said it is nothing but it's a product of transconductance into the output impedance. Now among these two parameters, we were dealing with just how to compute the output impedance. Now that it's time for us to compute the transconductance of any device. Okay. So now let us go with a very simple case, but before that let me try to define what is this transconductance, and then later we'll use this transconductance definition onto the circuit and then figure out what is the GM of a given circuit. Okay. Now this is for the entire circuit. Okay. We are not talking specific to a particular transistor. Yeah. So consider that we have a two-port network and it has some sort of Vin at its input with plus and minus and whatever it is, and then it also has some sort of output port Vout with plus and minus. Now we know that this transconductance is nothing but it's something that relates to an output current with an input voltage. Am I right? That's how the transconductance appears. Even this GM was defined as for a transistor. This is for a transistor and this is for the circuit I'm talking. For a transistor, how was this GM was expressed? Yeah, it's a small ID, a small signal ID divided by VGS. Okay. So this VGS is nothing but the input and this ID was nothing but the output, right? So output current. So even this quantity has to have the same similar mechanisms or the same similar formalisms. So due to which I need I out here, which is the output current of the circuit, divided by the Vin of the circuit. Okay. And this is what I needed. Now how will I get this quantity out of my circuit if I have this as my two-port network circuit? And inside this we might have some sort of voltage control current source. Say for example I have this guy and due to this Vin there might be some sort of current source. Okay, let me label this as something like Ix, and it can also have some sort of resistance R out. Okay. This is a general circuit that you generally have it inside this particular box. Okay, and this Ix could be something like voltage controlled current source. Okay, the only thing that I'm worried is how to extract this I out parameter from the two-port network. Short the, yeah. So exactly, whenever you want to measure any current, what you do is that you need to make the current to flow through the device and through an ammeter. So which means that you need to short those terminals. Okay. So whenever you short this particular point, what happens is that the Vout goes to 0, but obviously you will end up having some sort of I out current. Okay, through this short circuit. And in general, I can state this I out is nothing but it's a short circuit current. Okay. Okay. So once you have this I out, then one could define the I out in terms of Vn, depending on what type of current sources you are dealing inside the circuit. Okay, if it is a voltage controlled current source, mostly we will be dealing with voltage controlled current source. Through this voltage controlled current source, I could relate this I out to my Vn. Okay, is that clear? So now let us take a very simple circuit, and then we'll just move on to the complicated circuit after this. I have this Vn and I have this Vout, and it's nothing but a CS amplifier. And I just want to compute the capital GM of the circuit. First I need to draw the small signal model. So I just begin with gate and then the drain. So I just mark this drain here, and then the source which is connected to my ground. Now that I have some sort of VGS with plus and minus, where the gate VG is connected to my Vn, which is small signal. Okay, and obviously the drain is connected to some sort of load, which is the resistance, and the other end of the resistance is obviously translated to some sort of AC ground. So due to which I have this RD getting connected to my ground, and this is my Vout. And in between this drain and the source, just because of the polarity of my VGS, I'm just going to draw the current direction to flow from drain to source as GM VGS, and then we have something like an R0 in parallel. Okay, so this is a circuit setup that I have, and now that for this circuit I just want to evaluate the transconductance. So what you do is that step number 1 is to short this particular Vout, and in a way I'm trying to measure what would be the output current. Now can you guess what would be the value of it? Is it GM VGS or sure? No? Yeah, minus GM VGS. Okay, you have to be clear with this. Just because the current is flowing in this direction, but we are expecting a current in the opposite to get flowed, okay, due to which it becomes as a negative, okay. Yeah, so what about these resistance? Will the current won't get diverted in these paths? No, why? The potential at this point and the potential at this point are the same. So whenever you have a resistor with both these voltages VA and VB are equal, no current would flow. Okay, the current would then become equal to 0 whenever the potential across both these nodes are equal. Okay, so that is the concept that you are going to use it. So in both these resistances, the potentials are same, due to which none of the currents would flow. The other path that I have is this I out, and due to which the current would flow through them. Okay, so this entire current has to loop around something like this. So now one could write this I out as something like minus GM times VGS, and I need this VGS to be expressed in terms of Vin. So I use the same formula of expressing the VGS as VG minus Vs, where the VG is connected to the Vin and the source is connected to my ground. So VGS is nothing but my Vn. I plug in those and I can extract the value of capital GM to be equal to I out by Vn, and that is nothing but minus GM. Okay. Yeah, so there is one thing that I want to emphasize here is that in your textbook the gain was expressed as something like minus capital GM times R out. Okay, this is your textbook notation, but I generally prefer to use this kind of notation where I am trying to define this GM to be this gain to be just a product of capital GM times R out, or in short it's PNR's notation. So okay, is that clear? I'll be following this. If you, in case if you want to get back to your textbook and see that something is different, it is just because we are both the author and me are using two different notations. That's it. Okay. And most of the things would be inverted in the case of a textbook. I use a composite signal in a completely different way. In the textbook, I guess it was capital V and then small letter I out, out. Okay, so I'm using in a completely different way. Okay. Any doubt in this? No? Okay, so let us do a small exercise of this. And let's put some sort of resistance here. Yeah, so compute the transconductance GM of this device. Done? I don't remember the formula, so I have to do that and then get you an answer. But something, it's supposed to be a GM divided by some big term, okay? Because the final result supposed to be, cannot be a constant or a number. So the unit of this entire expression supposed to be in terms of GM. And that could be divided by some sort of number. So if you have R has to be followed by GM in order to create a number, okay? But at the top, you have to have some GM form. Okay, so what I really mean is that I have to do that. Are you clear? Shall I do for you? Okay, so let me translate all of these points of gate, source, and the drain, and then let me first create this polarity of my VGS, and I start drawing this current of GM VGS. And do I have body effect? It has, right? The source is not at the ground, so due to which I also have to consider this one. Okay, it will not be a GM dash directly just because of some reason. Okay, so I'll just write that and later I'll show you. Okay, so this entire thing that I've drawn is only the model of my MOSFET. Okay, now that I'm just going to add the component of resistors of RS and RD here. okay, and this is my V out. Now I just want to compute the I out, okay. Now what currents would flow through the device? In the sense, I have this I out even here, because this current I out cannot flow through this RD resistance, so what I have is this, and one could write this I out as summation of three current components, am I right? So I write this as I out to be equal to minus GM VGS, and then minus GMB VBS, and then the current through this guy. And how will I write the current? Yeah, what is this? So if I consider this as my VS divided by, or VS minus something. Yeah, VS minus 0, because this node is at the ground. So it is just the VS divided by R naught. Okay, the current is flowing from VS, yeah. So now let us express this VGS in terms of the known quantity. So before that, let me even write this VS. What is this VS basically? VS is nothing but the drop across the resistance RS. Okay, so what current? Yeah, I out is flowing in an opposite direction to a positive polarity, right? So it has to be returned minus I out times that of RS. Okay, so due to which, let me try to redefine my VGS as VG minus VS, and again what happens is that this VG is nothing but what is connected to my gate? Vin. Okay, so Vin minus this VS, where again I have this minus of I out times RS. Clear? So the entire VGS would then return as something like this. Okay. Now let us try to evaluate the expression for VBS. Now this VBS is written as VB minus VS, and where is my VB is connected? Ground. Okay, so due to which I will have only the VS term, and when we do all this manipulation, we end up having something like plus I out RS. Okay, yeah. So now that I have got all of these terms, I just plug in those expressions here. So this becomes like GM times that of Vin plus I out RS for my VGS, and then minus GMB into I out RS, and then I have this which ends up having minus I out RS by R naught. Okay, any doubt in this? I have re-expressed all this VGS and VBS with in terms of I out times RS. Okay, I think all these things are network theory. To be frank, nothing to do with our course. Okay, but you should be in a position to be much more familiar with this. Yeah. So now that you got the entire expression in terms of quantities that are required, the only thing is you need to pull out certain like do some sort of algebra, bring I out in one end, and use your Vn to the other end, and then use this I out by Vn expression to get it. Okay, so in this case I would get something like GM RS, GMB RS, and then RS by R naught, and the whole of this has to be multiplied with I out, and over here it is minus GM Vn. Okay, yeah. Okay, so now that I have to evaluate I out by Vn, and that is nothing but my capital GM, and that returns me minus GM divided by the whole lot of this expression. So again, this entire quantity that I have as a denominator, if you see, the one is a number. What is the product of GM and RS? Does it have any unit? No. Okay, so again it's a number. This is again a number. This is again a number. Okay, so what has happened is that the unit of this capital GM and the unit of this GM is the same, like Siemens. Okay, so that never changes, but what is dividing at the bottom is just a number. So I just have something like GM RS or GMB RS and R naught. Okay. So now that I just bring this R naught, multiply across all the numerators, and then I would end up having something like minus gm R naught divided by R naught, and I can combine this gm and gmb, so it would be like gm prime R naught rs plus rs. Now what is this quantity that we have at the bottom? The denominator. Output impedance whenever we look down, right? So we had a circuit and we discussed that if there is a resistance Rs, I said this Rs would be magnified by a quantity of gm prime Rs R naught, and then I still add this R naught and this Rs, okay? And this expression is nothing but the impedance that I look down from the drain is what I have, and this expression is identical to what I have written down here, okay? So if you could be able to think about that, if you could be able to recollect those kind of things, then it becomes easier for you to write the GM, capital GM, okay? Is that clear? The only thing is that this is a resistance. I need to divide the entire resistance with some sort of R naught or an ohms. Clear? So that's the reason why we have this R naught at the top. Clear? Does it make sense? Any doubt? Okay. So I'll stop here. In the next class, we'll start with the CS amplifier.